Hello class, welcome to the next lecture on control systems, and today we'll be talking about mechanical systems and how you can find the transfer function, and later we'll see how you can convert them into electrical systems. Okay, so first of all, mechanical system, what are they? They are basically interconnection of mechanical physical items like springs, dampers, masses, torques, things like that. Okay, so we can classify them into two, that is translational and rotational. And what do you mean by translational system? That is, motion is taking place in a straight line. What about rotational? Motion is taking place about a fixed axis, that is, something is rotating. Okay, the force, the input will always be a torque for a rotational system, and the input will always be a force for a translational system. Okay, and the outputs we are considering is displacement for a translational system and angular displacement for a rotational system. Right, now the variables that we have to consider in a translational system are acceleration, velocity, and displacement. And what about rotational systems? Angular displacement, angular velocity, and angular acceleration. Now I'm just going through the basics. The main equation that governs the translational system is the sum of the forces will be equal to mass into acceleration, F equal to ma. Similarly, in rotational systems, sum of the torques will be equal to the inertia of the whatever mechanical mass is there, that inertia into the angular acceleration. Right, and moving on. What about the elements? We have mass, which is usually usually shown as a rectangular box. Okay, we have friction or a damper, which is shown like this. Friction is usually represented using a damper like this. Then we have a spring, which is shown like this. Okay, equations governing mass is equal to F is equal to ma. And what about damper or friction? F equal to d into v or d into dx by dt. Similarly, for a spring, it is F is equal to kx. Right, x is the displacement. And when we come to this rotational system, we have tau equal to j alpha, where tau is the torque and j is the inertia, alpha is the angular acceleration. Right, and similar to damper in translational system, we have a damper in rotational system also. Here also it is tau equal to d omega. It is similar, it is very much analogous only. And torsional spring, we have tau equal to k theta, where theta is the angular displacement. Okay. Now let's see an example of what we mean. Okay. Here the question is, find the transfer function for the given mechanical system. Okay. Now this is a translational system. We have a fixed surface. Okay, this is a fixed surface. Then we have a spring and a damper connecting a mass to the fixed surface, right? And the value of the spring is k, and the value of the damper is d, and the mass is m. And then a force is applied on the mass, and that force creates a displacement. That's why we have the input as f and output as x. So what we're doing is, we are drawing the free body diagram, that is the mass with the different forces acting on it. So right away, F, the applied force is acting downwards. This spring and damper acts opposite to the applied force, that is upwards, Fk and Fd. Okay, so our equation is sum of forces equal to ma, mass into acceleration. right? So we are taking a direction into consideration here. So f minus fk minus fd equal to ma. Okay, so that is we can move this into these two into this side. So we have f is equal to ma plus fk plus fd. Now earlier we have seen what was the equation representing the force of spring and a damper. That is for a damper it was dv, and for a spring it was kx. So everything we are representing in terms of x. This is our output variable. So we have f is equal to m d squared x by dt squared plus dx by dt plus kx. We are taking the Laplace transform. So we have f of s equal to m s squared xs plus ds xs plus k xs. Therefore, the transfer function is x of s by f of s equal to, cross multiplying, we get 1 by m s squared plus ds plus k. This is how you get the transfer function for a translational mechanical system. Okay, it's pretty simple. All you have to do is draw the free body diagram and write down the equation, find the Laplace transform, and just take the transfer function. Okay, now let's see something with two nodes. Okay, that is, we are considering the displacement at two different points. Here you can see two masses are there, and one mass is connected to the surface using a spring and a damper. The other mass is connected to this mass m2 using another spring, and the force is applied to the last mass. Okay, now consider x1. Okay, considering x1. So at x1, node at x1, this one, what is happening? We have a force F downwards, and the spring applies a force upwards, that is Fk1. So F minus Fk1 is equal to m1a1, F is equal to m1 d squared x1 by dt squared plus k into x1 minus x2. This is our first equation. Similarly, at node 2, what can we do? Here at node 2, what we do is, right here also we write the equation. So this spring is applying a force upwards, right? That is shown here. Then similarly we have the spring and the damper applying forces upwards to this particular mass. So we can write the equation as minus Fk2 minus Fd2 minus Fk1 is equal to m2 a2. So writing everything in terms of x, we have 0 equal to m2 d squared x2 by dt squared plus d2 dx2 by dt plus k2 x2 plus k1 into x2 minus x1. That is our second equation. Now what do we do? Now what we do is we directly find the Laplace transform for both this equation 1 and equation 2. Right? We just represent as fs equal to something as the Laplace transform, and 0 equal to something in the Laplace transform. Now, what do we want actually? We want the transfer functions, right? Actually, we have two outputs, x2 and x1. So one transfer function will be x2 by f of s, and the other will be x1 by f of s. So this for us right now, to find the Laplace transform, these are our two base equations. So to find the transfer function, what we do is we substitute for x1 to, that is, we substitute for x1 in terms of x2 from equation 4 in equation 3 to get x2 by fs, and we substitute for x2 in terms of x1 from equation 4 to equation 3 to get x1 by f of s. That is what is happening here. Okay, that is, here what are we doing? Here from this equation we have found x2 equal to something as a function of x1, and that we have put here. Okay, here instead of this x2 we have substituted whatever we have got here, that is this one. From there we have grouped the coefficients for x1 and we have cross multiplied with fs, then we are getting the final transfer function. We have done the same thing for x2 also, that is we have from this equation we have found the value for x1 equal to some function of x2, and we have substituted it for here all these, both of these x1s. Then we have fs equal to a function of x2, right? That is what we have done here. And finally we have found x2 by f, that is our second transfer function. Okay. Now let's see a simple example for a rotational system, right? So here this concept for rotational systems are the same, just that instead of thinking in straight lines we have to think of rotational things like torque and angular displacement and angular velocity and stuff. So here right away we can write our this is our free body diagram. We have one torque like this, right? Torque like this. We have our two forces opposing it like this, Fd and Fk. So here D is the friction. Okay, here we have a friction and we are modeling that friction as D. So we have tau or T, whichever suits you, is equal to J into d square theta by dt square plus K. This is actually, this rod is actually torsional spring. Okay, K theta plus D theta by dt. We have found the Laplace transform, and from that theta by tau. Okay. Now the next topic is analogous systems. That is, we can represent mechanical systems in using differential equations, right? In terms of the spring constants and the dampers and masses, inertia, angular velocity, angular displacement, linear displacement, things like that. Similarly, we can represent the electrical systems, electrical networks in terms of voltages, currents, resistance, inductance, capacitance, things like that, which are also differential equations. Therefore, by comparing and finding an analogy between these two systems, we can convert our mechanical systems into an electrical equivalent. That is what we mean by analogous systems. That is, we can find electrical analogous systems for mechanical systems, and vice versa. We can also do the other way, but for the interest of this paper, we are looking at only how to convert mechanical systems into analogous electrical systems, and that can be done in two ways. That is, we can equate the force to voltage and torque, or the force and torque we can equate to voltage, right? And the other way is that we can equate the force and torque to current. Both will result in two drastically different networks, electrical networks. Okay, so let's see how we come across or how we find out or derive at this analogies. The first one is force, voltage, torque analogy. So consider a series RLC network. Okay, we can write the equation as V equal to IR plus LdI by dt plus 1 by C integral I dt. Quite common. And here we are representing I as dq by dt. That is, we are trying to represent the variables in the most basic form. Okay, so instead of I, we will substitute with this. So therefore, V equal to dq by dt into R plus d squared by q by d squared q by dt square into L plus 1 by C q. Okay, now we can compare this to the what do you say, mechanical systems. where what do you say, f equal to m d squared x by dt square plus d dx by dt plus kx, and tau equal to j d squared theta by dt square plus d d theta by dt plus k theta. Okay, we can compare this as a direct comparison. It is possible. So from this we can see that if we are taking voltage as equivalent to force or torque, right, we can take these terms, right. If force is taken as voltage and torque, or if you're taking voltage as equivalent to force or torque, you can compare the coefficients of the second derivative, the first derivative, right. So here the basic term, basic variable is q. Here it is x, here it is theta. So q, x, theta, right. Similarly, if you look at it, the d squared term here, L is coming, m is coming, j is coming, like that. Similarly, for that, like that, we can do for all the different parameters of the network and the physical system, right. So this is just a shorthand, JML dr k by c theta x q. That is, if you are having a force voltage analogy, J, M and L are the three things that you have to interchange. That is, in the mechanical equation, if you have M, instead of that you substitute L for the electrical system. And if you have D in the mechanical equation, you substitute R. If you have K in the mechanical system, you substitute 1 by C. If you have theta or X in the mechanical system, you substitute Q. Okay, this is our force, torque, voltage equivalent. Similarly, consider a parallel branch, parallel RLC circuit with a current source. Write the equation and you will get the force, current, torque equation. Okay, force, current, torque relation. You can go through them. It is quite simple, so I am not explaining them in detail. Okay, now let's see a question. This is more important. The question is, find the force, voltage and force current analogous electrical circuit for the mechanical system given below. Okay, this is a system. We have a fixed surface, a damper, a spring, a mass, again a spring, a second mass and a force applied to the M1, middle one, and we have X1 and X2. Okay. So to convert this mechanical system into electrical system, you have 2 or 3 steps. So step 1 is to redraw the mechanical system into a nodal form. That is, we are redrawing it like you draw a network. Okay. So if you look at here, the first of all we create a reference surface. Okay, reference surface. We attach all the masses and forces into the reference surface. Okay, then we have 2 nodes. Why? Because we have 2 displacements. If it was an angular system, I mean rotational system, we would have considered 2 nodes if there were 2 thetas. Okay, 2 angular displacements. I won't be explaining the rotational system separately because it is the same concept. Okay, anything you learn here for a translational system, you can apply it to rotational system. Right. Now, if you look at here, K1 and D1 are fixed at one end to the mass M1 and the other end is fixed to the this fixed surface. So D1 and K1, we are fixing one end at the fixed surface and the other end to this node, right? And mass, it is at M1 that we are finding X1, right? We are taking X1, so mass is also connected to X1. Since these are connected to M1 and we are taking X1 here, the one end of these are also connected to what? The node x1. At this side, if you see, the mass is connected to the ground or the reference surface, reference node. The force here, this one is also connected at one end to here, the other end to the node where it is being applied. And this one, K2, it is connected between two masses, that is between two displacements. So that is also connected between two nodes. That is how you get the nodal form of a mechanical system. Okay. Once you have this, it is very simple. You can write the differential equation for each node. Okay. By using what equation? The same equation, force equation that we have done earlier. So at node x1, what is happening? F equal to m1 d square x1 by dt square plus k1 x1 plus d1 dx1 by dt plus, you have to consider for this also because it is connected between x1 and x2. So k2 into x1 minus x2. You can rearrange this into whatever form you want. That is our first equation. So I think right away you can find similarities between how you are writing this differential equation and how you will write the equations for a nodal analysis of an electrical network. Okay. Similarly, at node 2 you can write what? At node 2 what is happening? Only m2 is there. So m2 d square x2 by dt square plus we have k2. Okay, k2 is connected between x2 and x1. So k2 into x2 minus x1. So that also what you can do, you can rearrange and form equation 2. Now you have to convert it into the electrical system. These two, these equations are your base. Okay, it is using these equations that you convert them into analogous systems, analogous electrical systems, and that depends on first of all on these equations and what kind of analogy you are taking. Okay, so first let's take force voltage analogy. So we have JML dr k into 1 by c theta x cube. Okay, so our equation 1, which is this F equal to m1, that one, that equation becomes F will become V, M will become L, this D will become R. See, M will become L, D will become R, and X is becoming Q, right, Q1. Similarly, K will become 1 by C, C1 and C2, K1 plus K2 becomes 1 by C1 plus 1 by C2. X1 will become Q1. Similarly, K2 and X2. Right, this is our equation number 3. And what happens to equation 2? This one, M2 will become L2, K2 will become 1 by C2, right? And again, K2 will become 1 by C2. It's a direct one-to-one conversion. We just have to change the variables. Now, the task is, you have two equations representing a electrical network. How do you draw the system, right? So here, this first of all, you can convert all this dq by dt's into I. So d square q will become di, and dq by dt will become I. What about q? It will become integral I dt. Okay. So here we have rewritten the equations. Now we want to write we want to draw the equivalent electrical system. Okay. Now if you see, V equal to something, V equal to LdI by dt plus Ri. If you look at this, all these are voltage terms, right? LdI by dt, Ri, 1 by C I dt, integral I dt, right? Again, all these are voltage terms. So basically, we have written a mesh equation here. So how do you write the equivalent one? Here we have V equal to L di1 by dt plus R di plus 1 by C1 plus 1 by C2 plus integral idt. So you can understand that all these L1, R1, C1, C2, okay, let's forget C2. L1, R1 and C1 are in a loop which only has what? I1 and V. Similarly, C2 is having both I1 and I2. That is, it is a in-between loop, in-between path. Okay. Similarly, coming to the second equation, we have L2 which is only having I2, but again C2 we have already found that it is having an in-between path. That is, it is being influenced by both currents. So this is the equivalent equivalent electrical network for a force voltage analogy. Now let's see the same thing using a force current analogy. Okay, so using this analogy, you will get the final equation as I equal to C1 d V1 by dt plus 1 by L1, like this. So from this you can see that this is a nodal equation. Okay, this is a nodal equation, and that C1, L1 and R1 are at node 1, at a single node, and this C2 is at the other node, and this L1 is in between these two nodes. So that is what we have here, right? What do we have? We have, right, our current I, C1, L1 and R1 connected to node 1, C2 connected to node 2, and L1 in between these two nodes. So that is how you take a mechanical system, you redraw it into a nodal form, you write the force equation, you use the analogy shortcut that we have created earlier to find the analogous differential equation for the electrical system. You identify whether it is a mesh equation or a nodal equation. Then you redraw the electrical system depending on the equation that you have. Okay. Let's see one more problem. The question is, find the force voltage and force current analogous electrical system for mechanical system given below. Okay. So how do you draw this one? The K1 you will connect to the ground and node x1. M you will connect to ground and node x1. Right. D1 you will connect to ground and node x1. Okay. M1, M2 you will connect to ground and node x2. D2 you will connect to ground and node x2. Right. Force you will connect between ground and node x2. Then D3 and K2 you will connect between node x1 and x2. Okay. Now we will write the equations at x1 and x2. Pretty much how we did earlier, like the summation of the forces. Then once we have these differential equations, we write the force voltage analogy, and we substitute for F, D, X, M, things like that. Then we have a network equation, right? So depending on whether it is a loop equation or a nodal equation, we write the equivalent circuit. So always for an FV analogy, it will be a mesh equation, and always for an FI analogy, it will be a nodal equation. Okay, here are some problems, homework problems for you. So these are pretty much similar to what we have done, just that you have to be careful when you're converting it to the nodal form, then it is easy. Okay, for this rotational system, it is pretty much the same. Okay, just consider, just take tau instead of, that is torque is instead of force. How will you draw the torque? Between the reference node and theta 1. Instead of x, it is theta 1. So torque will be between ground and reference node and theta 1. J1 will be between reference node and theta 1. D will be between reference node and theta 2. J2 will be between reference node and theta 2. K will be between theta 1 and theta 2. Right. Similarly, this motor, it is having a torque as well as a inertia Jm. Okay, so this is a 3-node system. Theta 1, theta 2 and theta 3 are there. Right. And this one, the only difference for this one is that here 2 wheels are given. So it is rolling, and rolling means no friction is there. Rolling friction is negligible. So we don't have to model any dampers for this friction. Okay. So that is it regarding electrical equivalent of mechanical systems. Thank you.